afternoon, everyone. I'm Helen Rosenfeld. I'm the Executive Director with the Massachusetts Science and Engineering Fair. Very excited to have today's speaker series continue with Lei Pu from Analog Devices. And I'm just going to do a few quick housekeeping items, and then I'm going to turn it over to her. We'll do a Q&A towards the end. Everybody's screens and audio is on mute, but at that point, if you want to message the chat with your questions, I can either read them out loud or I can take you off mute and allow you to ask your questions directly. So we will loop back with those instructions later, but I just wanted to give you a heads up. This is meant to be interactive as we go, and I welcome your comments. And with that, thank you so much for joining us today, Lei.
You're welcome. Hi, everybody. So Helen, are you going to have my slides pulled up, or should I pull up my slides?
I enabled screen share, so if you'd like to do it, otherwise I can pull them up.
That's okay. I will pull my slides up. 1 second. And let me know if you can see it.
We can see it.
Okay, let me put it to full screen. All right, so hi everybody. Definitely an honor to be here to share my experience. Let me introduce who I am. And I'm gonna move my screen a little bit further down here. So I am a systems and security architect at Analog Devices. I'm an engineering manager of a team of seven very creative and very experienced individuals. And we're all part of the Automotive Business Unit at ADI. So the sector of industry that we service is really about cars, vehicles, transportation. A little bit about my personal background. So I do have 15 years in the semiconductor chip industry. I've collaborated with a lot of really smart people over the years. So I do have 19 patents resulting from that, from that collaborative work. Before I joined Analog Devices, I worked at NXP, Broadcom, and Marvell Semiconductor. So you may or may not have heard of these companies before, because a lot of the products that these chip companies do go into device companies like Apple. So you probably would have heard of Apple, but not the individual component supplier. But these different semiconductor chip companies that I've worked for, they service different industries, right? So NXP and Broadcom, they service a variety of connectivity solutions, and they service the finance market as well for e-payments. And Marvell Semiconductor is really a big player in storage, right? In the storage industry. So they service a lot of disk drive manufacturers and flash drive manufacturers. Now, when I was in college, both doing my undergraduate and my graduate, I did intern at a few places as well. I had fun internships at JPL and Caltech for 2 years. And I did an internship at Xerox PARC, working on something totally different. And back in my undergraduate days, when I was at the University of Cambridge, I had an opportunity to work for AT&T Research Labs, where we did a really cool project about triangulation and locating someone in a building. And I would say that a lot of these internships, if you had the opportunity to apply for one, or if you did one before or planning to do one, many times you'll find that they have nothing to do with the eventual work that you will do in your career path, right? But they do add up to the experience. They do add up to build your character. So they're extremely important. And just a little bit of tidbit, I'm not originally from the US, so I'm from a small island nation called Singapore, and which has very, very different weather from the rest of the world, right? Because we're at the equator. All right, now I wanted to go a little bit to the next slide on what I do, because I think this gives you some perspective on the work and my work as an engineer at Analog Devices. I pulled up this picture because this is very, what I do is very similar to what a building architect does, except that when an architect builds a building, I actually build a product. And just a little bit of information here. Like, if you remember what an architect does, the architect will talk to their clients to ask what the clients want for buildings, or, what features the client wants to add to his house. And the architect here is really responsible for the blueprint, right? He has to draw out the plan, he has to draw the layout, and he goes back to the client to make sure that things are satisfactory to the client's requirements. And the architect works with the rest of the construction crew to ensure that, the space is really built out the way the client wants, right? Now, if I take this analogy to building a product, then you can see the many products, like these consumer gadgets that I kind of put the little icons here, that are out in the market, and many of you may have come across some of these products before. That every product here is really a system, right? And when a company builds a product, we have to take it through a product development flow, right? And this is an example of a product development flow where we shape the concept of the product from stakeholders, who want this product to be built, right? They give us some requirements, and we shape the concept of the product, and we flesh it out through a process that we call, architecture building and architecture analysis. And when we have a firm blueprint of what we want to build, then we take it to our designers, right? And the designers could be circuit designers. This could both be analog circuit designers or digital circuit designers. And we would actually implement them, right? And they become a form of a chip, a form of a board, right? And eventually we do testing. And once we've finished testing, that's when the product launch happens. Now I put a star here in the yellow box, and I'm sorry if the color makes it hard to read, right? The systems architect basically works in this region, right? It's like the go-between between the customer and the development crew here. And we have to specify how the product works, right? How it works over time, what it is made out of, and how the parts are all connected. And you can see that if we break this down, right, you can kind of bucket the 4 different lines here into 2 buckets, one that talks about function and one that talks about form. And this is really what architecture is all about. And when we start developing a product, right, we really do, the type of engineering that we do is called systems engineering, right, which leads to the next slide here. And I won't go into a lot of details about systems engineering. There's a whole course at MIT that you can eventually take on what systems engineering is. But I want to highlight that systems engineering is really about taking a system, right, and decomposing it into its subsystem and components so that you can achieve the desired functionality, right? And many times you have to employ a different set of thinking, which we call systems thinking. You have to think about how the different parts come together holistically, how it evolves over time, what are the causal relationships between each of the components, how to relate and act. And you keep in mind that the whole is really more important than the parts, right? That there's something of value that comes out from tying all the individual components together. And I want to give an example, which you may or may not have seen, right? Take an hourglass, for example, right? Effectively, if you decompose the hourglass, is made up of 2 things, right? Sand and a bottle, right? But if you had individually just observed the sand and the bottle, you may not have been able to extract, the timekeeping functionality that comes from combining the 2. So function emergence is really an important piece of systems engineering, right? We design a function, from components that you wouldn't have expected the components to be able to do, right? Now that you know systems engineering, I wanted to talk about security, right? Because I said I was also a systems and security architect. Now, looking at these pictures, hopefully it gives you a laugh, during a midday. And you're probably wondering why these pictures definitely do not add up to what they were intended to achieve. And it goes to show that, security, and these are examples of physical security. So security is really, a piece that has to be designed into any product, right? So to achieve its desired intent. So most of the time we do try to design in security as early as possible in the product development flow during the architecture phase. So the architect usually has to undertake some of these design principles. We definitely do not leave it to be after the fact, because, you know, by leaving it to be ad hoc, then, you know, people do get creative. They will still install things the way, you know, that it was supposed to do, but probably, you know, taking some, you know, creative measures, as you'll see here, right? I want to talk a little bit about, you know, how security is designed into a product, because that kind of gives you a feel for what I do on a day-to-day basis. I work with teams, different product lines. And, you know, part of my job is trying to ensure that security is designed into a product, and in what way. So you can see a five-step approach here, right? Ranging from system description to assets, to threats, security objectives, and, you know, security functionality, right? And we go through this set of questions that ask ourselves about what exactly do we need to care about in this product that affects the way a user would use the product, and it affects the way a hacker would try to hack the product, right? So starting with system description, we asked what the system is supposed to do, right? What is its function? What are the input and output interfaces of the system? Who has access? You know, does the system rely on secrets that you have to store and guard within the system? And where does the system play a bigger role, right? And is it some smaller part of a bigger system? So is that a bigger picture that you can see? And then we ask the question, what are we trying to protect, right? You know, most of the time when we're designing, you know, products, right, it's most likely data, right? So if you look at your Amazon Echo, you ask yourself the questions, well, what do I worry about, right? Is it a safety issue dealing with people? Is it the data because I'm worried about somebody eavesdropping on what I'm talking in the room? Or is it some kind of IP, you know, which could be code that you created and you don't want it to be pirated? And secrets, right? Secrets where is your password, your authorization code that resides in that device. Then we go on to, once we have the picture, we go on to figure out what are we trying to protect against, right? You know, there are a lot of these different attacks that you may or may not have heard of. I think the most common that you may have heard is spoofing, right? And that's essentially having an attacker intercepting your data communication, you know, midstream and pretending to be you. So that could be an element of masquerading as the correct recipient. And there are many different kinds of attack at different levels. You know, some are more sophisticated than others. Physical type attacks tend to mean that you must have some knowledge about how to, you know, break into a system. But there are some easier attacks, like, you know, changing the history, right? Editing the code if you have access to the code, or maybe triggering a buffer overflows. For those of you who have done some programming, you know that sometimes when you write a code and you deliberately put the array index to be x+1 over the actual size of the array, you know, the code, when you run it, at runtime, you might be returned a value that is in a memory region that wasn't supposed to be accessible by the code, right? So these are different ways that can access a system without authorization. Now, once we have a picture of what we're trying to protect against, we kind of rank them in terms of how likely the attack is going to happen versus, you know, what kind of damage this attack is going to do. And once we have a relative picture of what are the important things that we need to do, we put together a set of security objectives for the product, right? You know, so this is basically telling us what level of protection is really acceptable and sufficient for this product that is going to go out into this specific market. There are markets where confidentiality of data is going to be important, right? You don't want to leak your credit card information, but there's going to be other markets where data is just raw data coming from some sensor, right? Of itself, there's no value because it doesn't point to a specific person or their credit card information. But what you really want is integrity over confidentiality, because integrity tells you that the data is really coming from where you were expecting it to come from. So with that in mind, once we have a set of objectives, right, we go on to flesh out, the features that are needed to achieve the objectives, right? Do we need to use some, cryptography? Do we need to set up some fault detection mechanisms, because a fault can trigger a different reaction? Do we need to sign our software images so that we can show our customers that the software is really coming from the intended, origin, right? So these are things that we care about when we build a product. Now, going back to my career path, now that I've explained to you what a systems and security architect does, right? I'm sure many of you would be wondering, right? Did I plan to get to where I am today? Was it intentional? Answer is no. And let me just walk you a little bit through my career path. So I kind of skipped a little bit ahead from college time to graduate postgraduate studies time, right? So I kind of started the history here on this chart from the time I graduated from my PhD years at Stanford. When I graduated, I like to tell the story here a little bit, right? To kind of illustrate to you that sometimes life kind of takes you in paths that you don't expect. So when I was a grad student, so in Stanford, you have to pass the qualifying exams before you would be admitted to the PhD program. And so everybody's admitted in as a master's student, right, in the electrical engineering department. And you don't get to be a PhD student and enter the PhD stream until you pass the quals. And at that time, when I was working towards, passing the quals, I had a friend who asked me if I wanted to step out, just start working, join the workforce, work for a company, and the company name was Google. And I would have been one of the maybe first, 50 employees. And I actually said no. So life kind of takes you through, different twists and turns. Had I said yes, I might have had different opportunities in life. But at that time, I passed the qualifying exam, and I said I wanted to stay. And, there was a general lack of confidence too during that time when I was in school, because it just happened to be a few years after the dot-com bust, right? So that was about the year 2000. So I lasted a few more years in grad school. When I got out, I interviewed at this company called Marvell Semiconductor. I gave them a talk on my work, and they gave me a job offer even before I graduated from school. So I just happily took it up. I didn't really look elsewhere. It was a decent paying job. Did I know what Marvell, what Marvell's products were? No. Did I know what a product development flow was? No, I really didn't know much about what Marvell and the chip industry really comprised of. So it was kind of a blank slate for me. And whatever I learned, I did learn on the job. And, and you can see that I didn't start out in security, right? I started out doing a lot of information theory and coding. And when I had the opportunity to kind of take on more in security during the time when, in about 2006 and 7, there was this industry rise in called the Trusted Computing Group, where they were trying to push security into laptops, into PCs, into electronics in general, right? And my boss basically said, well, you're kind of the most junior engineer in the team, so why don't you go and figure out this trend, because we don't know whether this trend is going to continue. So, I was probably the youngest engineer as well, right, participating in that working group. It was definitely an experience that, an eye-opener and quite an experience, learning from all these really other experienced architects who joined and participated in the working group. So, the years went by and I successfully chipped in knowledge back into the company, and I worked with different teams to design the security architecture of Marvell's first storage controller. And these storage controllers go into disk drives, like Western Digital disk drives, the portable drive that you see today that you can just buy and order from Amazon. And then fast forward a few years, when I got married, it was also the time when I felt like I needed to look for a different project because, I kind of successfully already completed the first. And I had an opportunity to move to San Diego, right, to work for Broadcom. And it was for a totally different segment of the market, right? They were designing IC chips, but it was targeted for the payments market, which was starting to be a trend due to the rise of the smartphone and the tablets that now we find so common. And when I went there, my boss at that time said, well, you wouldn't have to worry about the penny pinching margins. You would be really allowed to design to whatever level that you felt security really meant for this product. And I definitely took that as an opportunity to stretch my imagination. And I joined a great team, worked at Broadcom for 6 years before Broadcom was acquired by a different company. So that's kind of part and parcel of being an engineer, right? You may end up in companies that are acquired, and so you're kind of sold off to another company and you work for a different company. And I became part of Avago for a while. And Avago bought Broadcom for $37 billion, right, which was one of the largest acquisitions in the semiconductor world at that time. But my team was eventually sold to NXP. I worked for NXP for a year, continuing the work in designing this secure element chip. And after a while, there was an opportunity that came up in Analog Devices right here in Boston. And the position that was offered to me was really to help drive the secure silicon strategy, right? To kind of reset that and to lead the product security assurance effort, and to get the company all, moving in the right direction. And that's kind of what I've been doing for the last couple of years at Analog Devices. And it was only recently that I moved over to the Automotive Business Unit, where I'm now focusing more on, automotive related applications, right? So I want to do a time check here. So Helen, am I still on time? I can't seem to see the clock here.
Yes, so we're 6
5
minutes to the
okay,
hour,
good.
and then Q&A, but if you go a little over, it's okay.
Okay,
we're fine.
Okay. So I just want to illustrate a little bit more to, the products I've done, because I think that probably gives you a better perspective. So self-encrypting drives, right? When I was in college, that was around, the 1997 to 2005, there was no such thing as a self-encrypting disk drive, right? You buy a disk drive. If you lose a disk drive, you lose the data. And if you happen to store your credit card information there and someone else might have bought this from eBay, then, you just have to pick up the pieces, right, with the credit card company. So the use case that kind of drove some of the work that I did was this general trend where corporations really wanted to ensure that when employees lost a laptop, right, they wouldn't lose corporate data. And if you lost your personal laptop, you also wouldn't lose your personal information. So the features that we had to build into these chips, right, chips which drive the functionality of what a disk drive does, is basically data arrest protection, which means that when everything is powered down, everything is encrypted. So someone who got your data who got your disk drive wouldn't be able to break the cryptography that protects the data. And there was a second feature which we call cryptographic disk erasure, right? So if someone wanted to reuse your disk drive, right, the only thing they can do is wipe it clean, right? So if they try to use your disk drive they would have to reset the drive. And what this meant was it would wipe out all existing data by just changing the cryptographic key. And then the second project that I said I worked on at Broadcom was a secure element chip. So a lot of you probably have your own phones. If not, your parents and your siblings might have phones. And you can see that if you break down your cell phone functionality, right, today you can enable Apple Pay, which is just double click, and then it does a face recognition, depending on which version of iPhone you have. And that authorizes a payment, which will go through even contactless today, right? And so what enables the smartphone to run these secure applications like mobile payments, right? You know, how can you be sure that the information that you give it is going to be kept securely so that in the event you lose your phone, and I think many people do that sometimes, that your information won't be compromised, right? You know, how can you be sure that your sibling is going to take your phone and be able to authorize a payment on something that he or she wants? So, you know, the heart of security for a smartphone like the iPhone is really this chip called a secure element chip. So it is a microprocessor chip that is essentially a vault, right? It stores any secure sensitive data that's related to you securely. And when it runs the secure applications, right, it actually checks that the code is digitally signed, is something that you can trust. It checks that the authentication that is coming is live. For example, my iPhone, I think I have iPhone 10, and it does a face recognition, right, live. So you can't fake it. And it allows mobile payments to go through, and it manages the life cycle of your device, right? So a lot of the functionality that you see that is offered here is something that we have to work out how the chip is going to be composed of, right? And that's part of what the architecture, you know, definition effort entails. So I just want to wrap up because I think I'm on time. What is an engineering career to me, right? And I think I've illustrated that a little bit, hopefully from my examples, right? You know, definitely it's about following your passion. And if you don't have a passion, maybe it's about finding one, right? And as you probably noted as well, right? And this is something I'll say again, that is not something that the school always will prepare you fully for, right? You kind of learn on the job, you learn through experience, and you know, your experiences in the past through internships, for example, they build up your character, and that's what, you know, is likely to carry you forward, right? Not the knowledge, necessarily the knowledge that you learn in school. And many times I'll say that EQ matters more than IQ, right? You don't have to be the smartest person in the room to be the best engineer. You know, sometimes you want to be able to collaborate with people who are smarter than you because they bring a very different perspective to the way you think. And giving constructive criticism is something that's better than, you know, just, you know, criticizing, you know, somebody else's project, because, you know, you want to enable the collaborative environment, right? And then I think I also talked about having a nonlinear path in a career, right? So keeping your eyes open about the different opportunities that cross your path, you know, embracing them, you know, be open. I think that's a very important piece. I think my career, if I reflect, is sometimes exciting. Definitely when, you know, you successfully build a product with your team, when you prove a concept, when you solve a problem. It can be sometimes draining at the same time because, you know, engineering can sometimes be, you know, trial and errors, right? So you could have many failures that come before a single success. But if I look back and say, what are the best things about having an engineering career is really, you know, realizing that you can't build a product by yourself, right? It's really all about teamwork. And the best part is building a future together with other smart and creative people. So Helen, I'll hand it back to you. That's the end of my talk.
Great.
Thank you.
Thank you so much. That was fantastic. Such a great overview.
Yeah.
For everyone who's on, please know that there's time for Q&A. And you can put your questions in the chat box and I can either read them out or I can take you off mute and you're welcome to ask your question yourself. So while we're waiting for some questions, I'll start us off with a question about how did you discover your passion? What was it that prompted you to decide that engineering was your pathway? Was there something that happened in high school that sent you on that path, or was there some experience you had, or was it just, did you always know?
So Helen, again, I think sometimes we don't know, and I will say I started out not knowing. When I was in high school, I had this lofty dream of wanting to be a scientist. I wanted to solve problems. I enjoyed solving problems. I was good at math and science. But did I envision being an engineer and working in the specific, place within that product development flow that I showed? I had no idea, right? Definitely, I had spent some years trying to find what I was good at, what I should be doing. And, I think learning on the fly, embracing the different opportunities and not saying no to people who ask you for help. I think that gives you an opportunity to find out if you really enjoy doing the things, in different areas, right? Because many times I've had friends who are engineers who are kind of locked down to this specific tasks, right? If you were a verification engineer, you probably keep doing verification for 10 years, right? And, is this something that they enjoy doing? Maybe. But it's also about, if you helped other people with newer things where that's outside of your comfort zone, you get the opportunity to try it, right? And by trying new things when you're more junior, it kind of enables you to find what your passion is and where you think you really contribute the most to that engineering path.
Great, thanks. We have a question from Rachel that's sort of similar to what I asked, but perhaps you can delineate it a little bit more. So the question is why you decided to study electrical engineering. So perhaps you can speak a little bit about the different pathways within engineering and how one might discover where one's skills or interests align best.
Okay, so why did I study electrical engineering? So I will say that so my path is going to be a little different for those of you in the US, right? Because, I'm originally from Singapore, right? I took the British A-levels. I did not go through the US system. And at that time, Singapore had a very famous leader called Lee Kuan Yew. And the funny story is that, the moment that he told all parents during National Day that your kid should go and study engineering, then a lot of the parents in Singapore were all brainwashed into sending their kids to go and study engineering. So did I really have a choice? Yeah, maybe, but my parents were fully believed. They really believed that the kid, if you had to go overseas and study something, it should be engineering, right? Now, what type of engineering? When I went to study at the University of Cambridge, it was a very interesting experience, right? Because in the first 2 years, even if you were trying to major in electrical engineering, you had to take courses in mechanical engineering. You had to take courses in civil engineering. So I actually did a lot of building, actual, mechanical work, building bridges as part of my curriculum when I was studying at the University of Cambridge. And then eventually when you get to specialize, right, what they call specialize, right? Why did I choose electrical and, maybe even information sciences? I think I enjoyed programming. I think that's definitely something that I do enjoy doing. And I did enjoy, doing math. So if you were doing a lot of circuit design, fundamentally is really math, right? Trying to understand. I liked physics as well. So if you were doing some transistor design, right, you have to understand the physics principles. So I guess that kind of led me to naturally, go towards electrical engineering. But in the end, what I majored, I did not go into the typical transistor design. I did not end up moving towards the physics side of things. I still remained more, I would say, mathematically grounded, because I enjoyed more of the analysis, the data analysis and the statistics that were involved, right, using different techniques in a very applied manner. Hopefully that gives you an idea. Sorry if it's not the best answer here.
There is opportunity for follow-up, so
Yeah.
no worries.
Yes.
We have a question here from Hamza. Knowing that a lot of people are choosing engineering or computer-related fields as their focus, what would you say drives a lot of people out of that field? And then also, what advice would you give yourself to, what advice would you give to your younger self, perhaps at age 15?
That's a long time ago. Okay, so what drives people out of this computer field? Now I will say that um, when I went to college, right, I was pretty certain I did not want to just become a computer programmer, right? Because you know when you look at what the younger or junior computer programmers do, right? They drink, you know, they can probably last all night programming, and I've been through those nights too when I was a student. Um, I just felt that long term it was not something that I could keep up with, right? So if you were competing with the you know, younger generation of computer programmers where they could just survive all night or pull an all-nighter with a cup of Coke in their hands, then you know you have to ask yourself whether that's the kind of life you know you can sustain long term. And for me, it was no, right? I wanted to go into an area of engineering where I felt I could really make an impact, but it was also something where experience over the years mattered. That you couldn't just be easily replaced with, you know, a fresh grad from school who knew, you know, C, Java, you know, and some programming languages, right? These days, you know, it's more like Python and some of the newest scripting languages, right? Back in the old days, it was just C, Pascal, and maybe that gives you a hint for how old I am. What advice would I give to my 15-year-old self? I think I have a lot more advice to my 20-something-year-old self, but 15-year-old self, I think you want to try out different things. I think you want to keep an open mind, right? Keeping in mind that college is really a means to an end. You know, coming from a good college definitely helps in finding a job, but is definitely not, you know, the end itself, right? It's about learning continuously. What would I have chosen for my courses? I definitely would try to try different things, right? If I thought I was going to be an engineer, I'd probably tinker a lot more with things, because I think having the breadth of knowledge does help if you wanted to pull together some demos to show people, you know, tinkering is an important activity, right? Definitely I would pay a lot more attention to, you know, which school and what I wanted to do, read up a lot more as well, not be so focused, right? I think back in the days when I was in high school, you know, my dream was to be an R&D scientist, right? And in those days, you know, I think people worshipped scientists from Bell Labs, right? And these days, you know, you don't even hear about scientists from Bell Labs, right? That seemed to be an era that kind of, you know, has disappeared over time. I mean, we still have scientists in tip-top research labs, but, you know, they've evolved over time as well. And I think that, you know, one thing I would definitely ask my 15-year-old self to do is imagine the future, right? And at that time, I don't think I spent a lot of time imagining what the future could be, right? Back in those days, we already had bulletin boards. You probably don't see any of those anymore, right? But the closest thing to the internet before the time of the internet was bulletin boards where you could log on with a old rusty modem, and you could play some computer games, leave some, you know, messages for your friends who logged onto the same bulletin boards. So you don't have those anymore. And I guess we never really dreamt about what the future could be, right? And sometimes dreaming is an important thing.
Great answer.
Yeah.
Thanks. So we have a question here from Mantra. Were you involved in research projects as an undergrad or grad? And if so, do you have any advice on how to get involved with those?
Oh, okay. So yes, I was definitely involved in some research projects. When I was an undergrad, I applied to the internship program at JPL at Caltech. So this is something that a summer internship that Caltech organizes yearly. And I was fortunate enough that at a time they allow international students to participate. And you could basically select from a list of projects, right? And so that's one possibility, right? You look for opportunities that are advertised. But if you already knew what you were interested in, right, it really doesn't hurt to visit the school, have an opportunity to talk to the professor, talk to the grad students, right? And, try to find out as much information as you can. So many years ago when I was an undergrad, definitely becoming an engineer wasn't my top choice. I was either R&D, and then for a few years, I was extremely, extremely excited about quantum computing, right? And you can imagine that was like 10 plus years ago. So, 10 plus years fast forward, we still don't have a quantum computer. So that's really, really far out. And you just have to try out the different things, talk to the people, try to understand, and finding that opportunity sometimes means that you have to, take the initiative to go talk to people yourself, right? And it's okay if you don't get the response that you want, right? But if you don't ask, you'll never get.
I would love to ask one last question, which is earlier in your slide loop, you showed the design process. I think there were 4 categories of design, whether order or not. Perhaps you can share whether there are different people who focus on each of those, or if it's part of a process that one engineer might deal with in total.
Okay. That's a very good question, right? Because again, this is something that you don't learn until you're in the industry. So it's a good question. Definitely there are different people who work in different parts of this process flow, right? One person cannot do it alone, right? It really takes a team, entire team to create a successful project. And for example, the person who goes out to collect requirements is typically the marketing manager or the marketing person, right? So he will engage sometimes the architect to go talk to the potential customers on what features we need to add or what we need to build, right? And what the customer will pay for, right? So his focus is really the business side, right? What the customer will pay. And then there will be systems applications engineers, right? Who might be involved in creating a concept, a proof of concept before the actual product is being built. Because sometimes we do enter a new field, we have no idea how to build a product, we have no idea what works. So we might pull together a quick demo. And in this case, the type of engineering, the type of role is really a systems applications role. And as we get down to design, right, we have circuit designers, we have analog circuit designers who are really just dealing with, circuit design. And we do have digital design engineers who try to build, controller designs, right? So these are the controller blocks where everything is going to be digitized, right? There's no analog circuitry here in this case. And the digital designers write the code in a language called RTL, right? And once they're synthesized, they become the building blocks for the different components within a chip. Now, once we have that, we have layout engineers who actually have to lay out the design of the chip. So something like this is not, it doesn't happen by accident, right? We have to be very careful about utilizing all the space here. So we have layout engineers, and we have EM engineers who test the electromagnetic interference. We have engineers in manufacturing who deal with the manufacturing process as well, right? And they tell us, like, in terms of what the process is. And, you may have heard of Moore's law, where, previously the transistors was on a really, old process, like maybe 180 nanometers. And now we're going all the way down to 7 nanometers, right, for the transistor. So, and as part of product launch, we have people who test, whose main job is to ensure that the system is fully tested. So those are test engineers. And when the product graduates, right, this is when product launch happens. Then again, we have marketing folks and sales engineers who take that to the customers. And we do have people who are called field application engineers who service questions from the customer, right? So it's an entire chain, and there's a lot of interdependency, definitely.
Well, great. Thank you
Right.
for walking through that with everyone. And
Okay.
thank you, everybody, for your fantastic questions and for participating this afternoon. I want to thank you so much for being our speaker.
Oh, thank you.
This was really wonderful.
Right.
And for everyone who dialed in today, we have these talks every Tuesday, Wednesday, and Thursday for the next 2 weeks. Our schedule's on our website. And if you're interested in diving in deeper to any of the subject matter that was discussed today, please email us at info@scifair.com, because we can look at ways in which to provide additional programming that might interest you. So thanks, everyone, for the participation. Have a good afternoon.
Thanks, Helen. All right. Bye, everyone. All right.
Bye.
Thanks. Bye.